Let's measure things! A project by Anne, Elizabeth, Sophia, and Vivian. The other day, when I was sitting and daydreaming in Gen Bio, I got all caught up in math, and I began to wonder, how does one actually measure length? I mean, clearly rulers work for measuring the length of lines, and I can extrapolate to rectangles and all, but how do we measure something weirder? Like, how do we measure this blob-like shape? And what exactly can we measure anyway? In my daydreaming mind that day, I started with just the basics. So here's a point. Now we have a segment whose length we can measure as the distance between 2 points x and y. So now we know we can measure intervals. If they overlap, we can add them together. If they are disjoint, we can union them. Now here's a rectangle, which is made up of those very segments. Specifically, here we have a rectangle made up of segments whose lengths are all 5. We take the measure of the area of the rectangle, which is equal to 5 times 5, or 25. So now let's look at some completely disjoint sets. What happens when our open subset O is composed of disjoint intervals? Well, let's say O contains I sub 1, I sub 2, I sub 3, and I sub 4. I sub 3 and I sub 4 overlap, meaning they are not disjoint. Intuitively, we can combine them to make one interval that is disjoint from the rest of the set, and we'll call that I sub 5. Therefore, I sub 1 union I sub 2 union I sub 5 is equal to O, our open subset, and we can measure the subset of intervals. Now, let's talk about two different techniques we can use to measure a set of intervals, exterior measure and interior measure. Remember that we do care about the reals, but some ideas are easier to see in the reals squared. So, let's go back to the blob. How can we apply these principles to measure the area of this blob? Well, let's take what's called its exterior measure first. We will place a cover over the blob with a big rectangle whose area we know, 8 by 6.5. Clearly, our blob is smaller than 52 square inches. We've got our first guess at its size ready. Now let's refine that by gridding up our 8 by 6.5 rectangle into a series of smaller, almost disjoint rectangles whose measures we also know. We can use such a grid because none of its component rectangles overlap. As we talked about before, we would then have to go through the process of combining them. What a headache! With the gridding technique, we can continue refining our measure by following these rules. First, if a rectangle of known size is external outside the blob, then reject it. Next, if a rectangle of known size is internal inside the blob, then keep it. If we subtract the rejected squares from the original 8 by 6.5 rectangle, we get an area of 34.125 square inches. This is definitely closer than our first measurement, but we still have a long way to go. We can continue to improve our measurement by dividing up the rectangles that are partially external and partially internal and repeating the same process. As we keep dividing those rectangles, our measurements will approach the actual measure of the blob and thus become more and more accurate. When we've divided the rectangles as much as possible, we can cut it up along the edges of the smallest rectangles external to the shape, making sure to never actually cut into our shape. That gives us a pretty accurate exterior measure, the infimum of all possible covers of the blob. So now let's delve deeper into the idea of the infimum. What we basically did was measure the open sets or the collections of intervals to cover the shape E with them. And then we took the smallest number from this set, which is the infimum. So the exterior measure is this. We take all covers by almost disjoint rectangles, and we take the length of all those covers, and then we take the greatest lower bound of the length of all those covers. We have the original cover, and we keep removing the area, and so the smallest thing that covers the blob is the area. So now we can finally express this quantity by writing, the exterior measure of shape E is the infimum of the measure of the known blocks. The combination of the infinitely many possible blocks that cover its area will be the size of the exterior area. We can apply the same concept of exterior measure to measure a disjoint union of intervals, like the one we discussed earlier. We'll start by placing a cover over all the intervals. As our covers become smaller and smaller, our measure becomes more and more accurate.
So now that we've found the exterior measure, let's have more fun with interior measure. The interior measure is the closed set on the inside, as opposed to the open set on the outside. So what does this mean? Let's go back to our blob. We can divide up the inside of the blob into rectangles, as before, using the same rules to reject, keep, or further divide each rectangle. But this time, we cut it up along the edges of the rectangles internal to the shape, thus measuring the inside of the blob. We define the interior measure using a familiar format, only this time, instead of the infimum of all known measurements, we take the supremum, which is the least upper bound of the length of all those rectangles. In other words, we take all the rectangles that fit inside the blob, essentially the opposite of what we did for the exterior. If we compare the two cutouts we've made, the interior and exterior measures, we can see that they're a little different. If we added finer grids to each, though, they'd get pretty darn similar to each other in size. This leads me to an even more rigorous definition of measure, the Lebesgue measure. First, we must realize that there are different types of sets that we could try to measure. We have the reals and all their subsets, and then within that big set, we have the measurable set, and then a subset of the measurable sets, the countable sets. Clearly, though we can't measure everything, we can measure anything measurable. Well, obviously. The Lebesgue measure just helps us to define what falls into the measurable category. It says that though all objects have a closed interior measure and an open exterior measure, an object is only measurable if its exterior and interior measurements are equal. In other words, m upper star of e equals m lower star of e. That means that we can get rid of our clunky interior and exterior measure notation and simply say m of e to denote the measure of our object. Now we know we can measure a blob. But hold up, there's actually a second way to define the Lebesgue measure too, and it's more useful for defining the measure of the countables. For all epsilon greater than 0, there exists an open set O that covers E, such that the exterior measure of O minus E is less than epsilon. This means that as epsilon gets smaller and smaller, O will approach E. Therefore, if the set E is measurable, we can approximate the measure of E using O. Using the second definition of Lebesgue measure, I wondered, could we measure something more complex though, like the rationals? The grand answer I came to while we were packing up to leave class is yes. We assert that since the naturals are countable, we can assign a natural number to every rational number. We can list the rationals so that we have a sub 1, a sub 2, a sub 3, and so on. Now we can cover each of these rationals with an interval. We can define the set epsilon as the union of all these intervals, that is, the union of every interval around each a sub n, where n goes from 1 to infinity. If all these intervals were disjoint, we could add up the length of each interval to find the measure of the set epsilon. But because the intervals are not necessarily disjoint, there may be overlap between intervals. This means that adding the intervals might result in a larger value than the actual measure of the set epsilon. Therefore, we can conclude that the measure of the set epsilon is less than or equal to the sum of all the intervals, and since the sum of the intervals is equal to epsilon, the measure of the set epsilon is less than or equal to epsilon. With this in mind, let's look at the measure of the rationals. We write this as a sum of 1 over 2n, where n starts at 1 and goes to infinity, since we can make infinitely many refinements to recover, like in earlier slides. So we have 1 over 2 plus 1 over 4 plus 1 over 8 plus ... and so on equals 1. Therefore, we have effectively covered the rationals with a set of measure 1. But let's not forget our definition of the Lebesgue measure. For all epsilon greater than 0, there exists an open set O such that the measure of E minus O is less than epsilon. So let's pull a trick out of our pocket and multiply our expression by epsilon. That is, if epsilon gets smaller, it means we're taking smaller and more precise measures of the countable number points, making up the rationals. If we want to get as precise as possible with our exterior measure, then we could let epsilon approach 0. But because the measure of the rationals is less than epsilon, the size of the rationals themselves will end up between 0 and an epsilon that approaches 0, which means the measure of the rationals will also approach 0. Finally, we've reached this conclusion. Anything in the countable subset of the measurables has a measure equal to 0. This includes the rationals, the naturals, and any other set of numbers that we can count. It does not include the reals or irrationals, because they're so darn dense, they're not countable. Despite being infinite, the entire set of rationals is the size of nothing. Maybe next Gen Bio class, I'll move on to another question. What defines the unmeasurables?
There are 10 millimeters in a centimeter, 100 centimeters in a meter, 1,000 meters in a kilometer. There are 12 inches in a foot, 3 feet in a yard, 1,760 yards in a mile. There are 1,000 grams in a kilo, 16 ounces in a pound, 14 pounds in a stone. So now you know 1 inch equals 2.54 centimeters. There is 1.6 kilometers in a mile. For every 100 grams, you get 3.5 ounces. And 1 kilo is 2 pounds, 3 ounces. And just a little bit. So if you're 6 feet tall, that's 1 meter 83. If you're 5 feet tall, that's 1 meter 52. If you weigh 200 pounds,
This is Sven's dad.
that's almost 91 kilos.
Sven's not here.
14 stone, 4 pounds, no ounces. Measurement.
Are you recording?
Measurement.
No? Yes. This is a lie.
What we're saying here is that if you have these
Measurements, measurements, we use
if
them
you have two,
every
like, so this whole
day.
thing we're calling our subset, whatever that
There's
is.
so much marker.
I ate a ghost pepper today, intentionally. Is that going to show up in the bloopers?
Yes.
The pints can be a little confusing.
and then look back at it for reference. Sure.
There are 8 pints in a gallon, no matter where you live.
Hi.
But a
Hello.
U.S.
How are you
pint
doing?
is not the same as a British pint.
Say hi.
A U.S. pint is 473, and a British pint is 568. There are 16 fluid ounces in it.
Whiteboards are better than chalkboards. Sven, don't you think that's true?
I'm leaving now.